Hello, my name is Pádraig Geraghty and this is my final year project, the analysis of a total hip replacement. The aims of this project were to examine the causes of failure of a hip prosthesis, to identify what materials are best suited in a hip prosthesis, and to carry out a stress analysis of a hip prosthesis. Some of the causes of failure in a hip prosthesis are dislocation, loosening and wear. Dislocation can happen at any stage after a hip prosthesis has been inserted. Loosening can also happen at any stage of the life of a hip prosthesis and is caused by a component needing to be changed. Wear is caused by contact and usually occurs in the bearing component. It can also be caused by the body's internal environment. From research, I found that the best material to make the stem from was titanium because of its high Young's modulus, good compressive strength and the porosity of the material, which allows the bone to grow into it. The acetabular cup was also made from these materials for the same reason. I decided to make the spherical bearing from stainless steel because of its high biocompatibility and its excellent surface finish, which would help reduce wear. I decided to make the acetabular liner from ultra-high molecular weight polyethylene because it works well in the body and has a low wear rate when coupled with stainless steel. Here's the model that I use in ANSYS 14.5. The outside region here shows the compact bone. The inner region here shows the porous bone. The inner region inside this shows the bone cement. This long purple region here is the stem of the prosthesis. The round blue region here is the spherical bearing. Just above this is another blue region. It's the liner. The purple region above that is the acetabular cup. For this model to work, it had to be constrained. It was constrained on this bottom line here, in the X and the Y direction. It was also constrained on this key point here to allow the acetabular cup not to slip. A pressure of 6.485 kilopascals was placed on the acetabular cup. Also a displacement of -2 millimeters was placed on the acetabular cup. When all of this was done, the model was solved. Here is the stresses in the X direction. The highest stress on the X direction was 5.61 megapascals and the lowest stress was -5.8 kilopascals. It can be seen in the video here that the higher stress acts on the spherical bearing and the stem. Here are the stresses in the Y direction. It should be noted that most of the force will actually act in the Y direction. This is why the stresses are higher. We have a highest stress here of -26.1 megapascals and our lowest stress is -2.77 megapascals. Again, the higher stress is acting down through the hip prosthesis and not the bone completely. This is a zoomed in view of the stresses in the X direction. It should be noted that the higher stresses are acting right here on the neck of -27.8 megapascals. This is because there is a large force acting down through a small area, the small area being the neck. The bearing component will experience a large amount of stress because of the contact that happens in it. The stem is experiencing a large amount of stress, which is all too common in modern prosthesis. The ideal situation is that the prosthesis transmit a smaller force and the bone transmit the larger force. Wolff's law states that if loading on a bone increases, the bone will remodel itself over time to become stronger. But if a hip prosthesis is taking the larger force, the body will not need the stronger bone and will reabsorb it. Again, just to point out, the stresses will be higher in the neck because of the smaller force passing through it. And that is my project, and I thank you for looking at my video.